All right, so part two, we're going to continue with this this problem. So, since we have y, which is equal to this expression, which I know if I wanted to do this, I'd have to do the product rule, derivative of the first times the second plus the first times the derivative of the second. What I can do is I can take the natural log of both sides, and on this side, what I know is that this is going to be the natural log of 2x plus the natural log of that x plus 1 to the 1/2. So then this is going to be equal to the natural log of 2x plus 1/2 the natural log of x plus 1. So when you take the derivative of this, this is going to be 1 over that u, which is 2x, times the derivative of 2x, which is 2, plus, now this is a constant, so pulling it out, and the derivative of this is going to be 1 over x plus 1, and you know the derivative of x plus 1 is 1, so I don't have to write that. So what I get here is I get 1 over x plus 1 over 2 times x plus 1. But remember that that this is the derivative of this side. So this side also has to be the derivative. So what's the derivative of this? Well, the derivative of the natural log of something is going to be 1 over that something. Now remember, when you take the derivative of something that includes y, you have to multiply it by dy dx. So that's what we have over here. We have 1 over y times dy dx is equal to this expression. So if I want to find what dy dx is, just multiply both sides by y now. Dx is going to be equal to y times this 1 over x plus 1 over 2 times x plus 1. And remember what y is. Y is this expression here. So this is going to be equal to 2x root x plus 1 multiplied by this 1 over x plus 1 over 2 times x plus 1. Now this, I know that the product rule might be simpler in this particular case, but the idea is if your expression gets extremely tedious, that that this expanding using logarithms first is extremely helpful. So what if we have let's see what we have here. Let's say b. What about y is equal to let's go x sine of x all over say x squared sine of x all over x plus 1. So something like this, we know that that in order to do it, you'd have this is the quotient rule because the entire thing's a quotient, but the numerator, which is f, is also a product. So you know this is one of those that's mixed with both product and quotient rule. So what we can do is we can take the natural log of both sides to be able to expand this. And what we know is the natural log is, you take care of this first, so this is going to be the natural log of the numerator minus the natural log of the denominator. Now this is the natural log of a product here, so natural log of a product is going to be the natural log of x squared plus the natural log of sine of x minus the natural log of 2x plus 1. And then finally any powers to natural log of x plus natural log of the sine of x minus the natural log of 2x plus 1. So that right here is just the natural log of y. So now what we're going to do is we're going to take the derivative of both sides. So I'm going to take the derivative with respect to x of this entire expression here. So taking the derivative with respect to x of the entire expression is going to give us, well, this is going to be 1 over y times dy dx. Then over here we're going to have 2 times 1 over x, so 2 over x. This is going to be 1 over the sine of x multiplied by the derivative of the sine of x, which is going to be the cosine of x. And this is going to be 1 over that 2x plus 1 multiplied by the derivative of the 2x plus 1, which is going to give us 2. So that means dy dx is going to be just multiply this expression by y. So dy dx is y times this expression here, this expression. Now remember what y is. Y is this original thing, so this would be equal to x squared sine of x all over 2x plus 1 multiplied by that expression, that 2 over x minus cosine of x over sine of x. I guess I could have wrote that as cotangent, minus 2 over 2x plus 1. And what's nice about that, again, is you get rid of having to do that product proportional. So logarithmic differentiation. All right, the derivative of our other power. So what we're going to do is we're going to find the derivative of functions that are base other than e. So like instead of just doing e to the x, what if I have like a to the x? So I'm going to have the derivative of y, which is equal to a to the u. So in order to do this, what I'm going to start out with is, we're going to kind of prove this. I'm going to start out with a to the x. So if I have y is equal to a to the x, what I know is I can rewrite this a to the x as e to the natural log of a to the x. So this e to the natural log just cancels. So these two expressions are the same. And what I can do now is if I just look at this natural log part, you can pull out the x. So this is equal to e to the x natural log of a. So now if I want the derivative with respect to x of both sides, so the derivative of this is going to be equal to the derivative of this. So the derivative with respect to x of e to the x natural log of a, we know that this is just an e function now. And the natural log of a is just a constant, because that's what a is. A is just some constant. So this is going to be equal to the derivative. Well, the derivative of e to something is going to be e to that something, so times the natural log of a, multiplied by the derivative of the top. Well, the derivative of the top is, well, this is just your coefficient, so you can kind of think of this as like just a number. Say it's like 5. If this was just 5x in the top, if this just said 5x, then the derivative would be just 5. So the derivative of natural log of a times x is just going to be its coefficient, which is the natural log of a. Now we know that this expression right here is still this expression, which was the original a to the x. So this piece right here is still a to the x multiplied by the natural log of a. So our theorem is if y is equal to a to the u and u is a function of x, then y prime is going to be equal to a to the u times the natural log of a multiplied by the derivative of u. So this du dx is just the chain rule, because this could be like a to the sine of, well, like 3 to the sine of x. So in practice, example, determine the derivative. If I have y is equal to, say, 3 to the x, well then y prime is going to be equal to 3 to the x multiplied by the natural log of 3. Really what we have is you just have this, I kind of call it like a correction. You have like this base 3 correction. It's kind of how you have to fix this. So the idea is this also works with e to the x. We already know its derivative of e to the x is equal to e to the x. But if you use this exact same rule, y prime would be equal to e to the x multiplied by the natural log of e. And the natural log of e is just 1. So that's why the derivative of e to the x is e to the x. So this works for any of these bases. So my y is equal to 5 to the sine of x. So this is 5 to a power, because it's in the exponent. So y prime is going to be, well, the derivative of an exponential is the exponential multiplied by that base correction, by the natural log of 5. Now since this sine function is a function of x, you still have to multiply by the derivative of what's inside, so multiplied by the cosine of x. Now we also have, next one is the derivative y is equal to the log base a of x. So we've done the natural log of x, so the log base e of x. What I want to do is I want to do the log base a of x. So what we know is if y is equal to the log base a of x, I can rewrite this as the natural log of x all over the natural log of a using our base, change of base. Now remember, the natural log of a is just a constant. So this is 1 over the natural log of a multiplied by the natural log of x. Remember, this is a is just a constant, so 1 over the natural log of a constant is still a constant. So you could almost think of like if this just said 5, this would be kind of like 5 natural log of x. Now it's not. It's some decimal though. So when I take the derivative of this, dy dx is going to be the derivative with respect to x of this 1 over the natural log of a multiplied by the natural log of x. Now, since this is a constant, you can just pull out that constant and then take the derivative with respect to x of the natural log of x. And the derivative of the natural log of x is 1 over x. So this is 1 over natural log of a multiplied by 1 over x. So we usually write this as 1 over x, natural log of a. So then our rule is, our theorem, I guess, this is one of our toolbox. So if I say theorem, as long as you remember it, you don't have to prove it. You just have to use it. So if y is equal to the log base a of u, and u is some function of x, then y prime is going to be equal to 1 over x natural log of u times your du dx. And again, the du dx is just a general. So some examples. Determine the derivative. A. If y is equal to the log base 4 of x, we know that y prime is going to be equal to 1 all over x times the natural log of 4. So kind of the idea of this is we already know how to take the derivative of this thing, right? So kind of the idea is if you want to be able to take the derivatives of like e to the x or natural log of x, the derivative of e to the x is just e to the x. So it kind of gives you something easy to remember. You already know the derivative of the natural log of x, which is 1 over x, so this would be equal to that 1 over x. But with natural logs, when you're taking the derivative of natural logs, you have to divide by that base correction. So exponentials, you multiply by the base correction. Logarithms, you divide by that natural log of its base. Now remember, this is the log base e of x. That's what that means. So that's why this is the natural log of e. And natural log of e cancels to 1. So this is 1 over x. So again, exponentials, you multiply by the natural log of the base. Logarithms, you divide by the natural log of the base. So it's the same derivative, just divided by the natural log of the base. So what about y is equal to the log base 7 of x squared minus 4? Well, what we know is that y prime is going to be, remember it's a logarithm, so it's going to be 1 over x times that, well, 1 over whatever this is, x squared minus 4, multiplied by divided by the natural log of that base. So if this just said natural log, this would be just 1 over this times the derivative of this. But since this is a log base 7, it's still going to be 1 over that times divided by the natural log of 7, multiplied by the derivative of this x squared minus 4, which is 2x. So this is going to be equal to 2x all over x squared minus 4, natural log of 7. That's our y prime. So again, how I remember is what I know is if y is equal to e to the x, then we know y prime is just e to the x. But if y is equal to like 5 to the x, then y prime is going to be equal to 5 to the x times the natural log of 5. Same thing with logarithms. If y is equal to the natural log of x, you know y prime is going to be equal to 1 over x. So these are the things that we tend to remember really easily. But if I have y is equal to the log base 5 of x, then y prime is going to be equal to 1 over x divided by the natural log of 5. So do you see that base correction? I kind of say that with exponentials you multiply it, but with logarithms you divide by it. So it's the original derivative that you'd expect, except multiplied by the base correction. The original derivative that you expect, except that base correction's on the bottom.